here. And when I was invited to give a lecture at this conference, I thought that it's impossible for me not to accept this invitation because Professor Julian Wawrynowicz was, finally, he was my teacher, he was my neighbor, and he was also my friend at the end. And I think that what is why we are connected. So when I was a student at the University of Łódź, I was also studying mathematics in the beginning of 80s of the previous century. So you know how old I am, but I think that he was also my teacher at the moment there at mathematics, at the Institute of Mathematics at the University of Łódź. And I was very proud that in one moment I managed to be accepted for the lectures of Professor Wawrynowicz. Later, Professor Wawrynowicz told me the story that, of course, you know that Professor Wawrynowicz was fighting with the previous regime in Poland, and from time to time he was not able to lecture at the university. And for a moment, it was the branch of the Institute of Mathematics of the Polish Academy of Sciences. It was established in Łódź mainly for Professor Wawrynowicz, and you will be very much surprised that this branch was established in the flat at Narutowicza Street, and exactly in the same flat I was born a few years before it. So this was, I think, that we've been neighbors for the first time. Later, I was living next door to Professor Wawrynowicz at Radiostacja District of Łódź, at the same street of Krzywickiego. Okay, later, Professor Wawrynowicz was many times in a number of committees for my PhD students, and he was quite sick at the end of his life, but he was always coming to my office here at the Technical University. And when I was offering that I will pick him from his house, he was always refusing. But sometimes it was possible that we took him back to his house. So he was always very proud, and I think he also invited few of my PhD students for this conference when this conference was in November. So, okay, I'm very proud that I was a friend of Professor Wawrynowicz, and of course, I will always remember him. Okay, but going back to science, I will speak a little bit today on the Chimera states for coupled pendulum. And I think that you may know that for many years I'm working on the chaotic systems, the systems of coupled, mainly mechanical oscillators. And of course, the pendulum is a typical paradigm for the mechanical oscillator. And when you have the coupled pendulum, sometimes you can observe the situation that those pendula can synchronize. And there is also a very personal story about it, that when I was in the primary school, I was told by the lectures of physics that two mechanical clocks hanging on the same wall can synchronize, or will synchronize. And this was told by the teacher, and the teacher, well, I had a very good physics teacher in primary school at Kopczyńskiego Street, now close to the university. But on the same day, my grandmother sent me to go to the workshop of the clock master. There were several mechanical clocks on his wall. No two of them were synchronized. So I asked the clock master, have you ever observed the synchronization of clocks hanging on the same wall? He told never. I think you can find this statement that two mechanical clocks will synchronize on the same wall. I think the first who wrote it was Dick Feynman. He wrote it in the lecture notes in physics. But unfortunately, this is not always true. Oh, it's not done.
Closer.
Okay, thanks a lot. Okay, so. Okay. Magic.
This is technology. It's French.
Myszką trzeba kliknąć na ten i już powinno działać.
Okay,
This part of mouse. So
okay.
so this part is moving. First.
Okay.
So you can.
Okay.
So this arrow and this mouse. So
Okay. So now it's working. So I think here on this slide, you can find the number of my coworkers. I was working on this topic in the last 20 years. So you can see part of those are my former PhD students who are now professors, like David Dudkowski, for example. He was studying here mathematics at this faculty. And there are also the number of my friends who are working there. So many years ago, I was trying to repeat the Huygens experiment. You can see what Huygens observed. He took two pendulum clocks. He was the first one who patented the mechanical pendulum clock, which was operating quite accurate. Of course, quite accurate for the standards of 17th centuries. He was sick in the Rotterdam, and he was playing with two clocks lying in the bed, playing with two clocks. So he put two clocks on the wooden bar there and put this bar on two chairs. And he was claiming that these two clocks can synchronize. He was using the word haute sympathie for antiphase synchronization of pendulum. Okay, why this was the important problem? At that time, Netherlands was a great power on the sea, and the Netherlands ships were traveling from Rotterdam all over the world. And it was the problem to establish the position of the ship on the open sea. And there was a problem how to estimate the longitudinal position of the ship. To do this, you need to have the exact time, the time difference between the port of the origin and the current position. And it was necessary to keep the proper time. Huygens clocks were able to operate up to 48 hours without rewinding of them. So he was thinking that if two clocks would synchronize, the second one would keep the proper time. Unfortunately, this is not the true. The idea was not good. But anyway, this is more or less the first experimental evidence of nonlinear phenomena of synchronization. Okay, and what are the chimeras? I think you know that the chimeras are strange objects like this one, who are located on the roof of the buildings just to protect those buildings from disasters. Maybe now in the Lower Silesia, it would be necessary to put chimeras on the bridges just to prevent flow. This chimera was not so good. It was located on the Notre Dame Cathedral, and unfortunately, the cathedral burned a few years ago. But what is interesting, the objects like Chimera were known all over the world. I've seen Chimera in Andes, in Peru, in China, in Japan. Okay, so maybe there is something. What is the Chimera in the sense of the coupled system? So imagine that we have a group of identical oscillators which are coupled. And you can observe the strange situation in which some of them would synchronize and some of them would be uncorrelated with those synchronized and would behave in the chaotic way. So this is what is called the chimera in the world coupled oscillators. I can also mention that something connected with chimera was always present at our university. So the university was originally created after the Second World War, and at the time in which there were a lot of textile industry. And in this textile industry, there were machines like this, in which there is a moving metal part which is going from this end to this end, making noise. And imagine that in one room, you have a number of such machines, and when all of them are synchronized, you will have a terrible noise. And when I was studying at the university here, on the second side of the street, there was the textile industry, and it was a terrible noise which were disturbing classes we had at that time. So what the people were trying to do, they were trying to desynchronize at least part of them. So at that time, the chimera, the word chimera for in this sense was not known, but of course I can now joke that at this university, the people were always trying to create chimera. Okay, but going back to Huygens, we took two clocks, put them on the wall in the lab. There are the real mechanical clocks, not the electrical clocks where the motion of the pendulum is simulated by the battery. So these are the mechanical clocks. We took them together. Later, we repeated exactly the Huygens experiment. There was no synchronization. When we put this bar on the road, we put some oil on the table. In this situation, it is possible to observe both phase synchronization and anti-phase synchronization. But to have this synchronization, it should be the transfer of energy from this clock to this clock and vice versa. Without this transfer, this is impossible. And that's why it is important to have the small horizontal motion of this bar. Without this motion, the clocks would never synchronize. Okay, so we've been happy when we finished it. At that time, my friend Yuri Maestrenko came here to go, okay, 2 clocks is not interesting. We have to have 20 clocks. So I told him, you must be crazy how to couple 20 clocks. So we moved from clocks to the metronome. Mechanical metronome is exactly the same mechanism as in the mechanical clock. Of course, there is no the phase and not the hands of the clock, but anyway, the mechanism is the same. Particularly this escapement mechanism, which is making tick-tock in mechanical clock. Okay, we took 20 metronomes, we coupled them together using the rubber or lycra bands. We coupled each pendulum with the nearest neighbor, green line, and with the second nearest neighbor by the red line. We forced this system to oscillate, and we managed to observe some kind of interesting behavior. And I think that small problem with this movie, but I think you will shortly got to say. Okay, so you can observe this movie, and you will be able to. You will be able to see that there is a group of oscillators on the back side, which are oscillating with the large amplitude, and they are synchronized. Those in front are oscillating in the uncorrelated way with the other one, and they are not synchronized with them. So this is the example of the Chimera. And you can also observe when watching more carefully this movie, that the situation can change. Those which are oscillating with the large amplitude after some time would stop, and those which start to oscillate with the large amplitude. So there will be not only the Chimera state, but this Chimera state would travel around the Sept. So even playing with such a simple experiment, it is possible to observe this strange behavior of Chimera states. And what is also interesting here, I think that now we can go back to the main presentation. Of course, I will leave you this movie again and everything. Okay, so what is interesting? The equations of motion are very simple. You can write these equations. Of course, there will be 20 equations like this. The only thing which is not standard is this momentum. This momentum is the momentum given to the pendulum from the escapement mechanism. This momentum is nothing else like this tick-tock, tick-tock. Of course, this is discontinuous. But nevertheless, such the equations can be easily solved numerically, and you will be able to prove in the numerical simulations that the Chimera states can be also observed. What else? We can generalize this relation playing with the so-called Kuramoto equation with inertia. In the original Kuramoto equation is without this star. Kuramoto with inertia is with this one. So if you look at this equation and the equation which I shown on the previous, it is some similarity, and that's why it is also important to study the Kuramoto equations with inertia. And I think we consider such parameters that each node, each oscillator was connected with the p number of nearest neighbors. And finally, it is possible to observe a different type of behavior. So, for example, it is possible to observe such a situation in which we have a nice synchronized group, and we have the oscillators which are uncorrelated with them. So such a situation is called the Chimera with one head. Of course, you can imagine that such a strange object as Chimera can have many heads, yes? So you can have the situation when there are three groups of uncorrelated oscillators. So this would be the Chimera with three heads and so on. Playing with some parameters of this Coulomb equation, you are able to find the region in which there exists the complete synchronization, all oscillators synchronized. You can observe the rotating wave. Rotating wave is something which you can observe during the soccer games when all supporters were happy, singing something and oscillating around the stadium. So this would be something like rotating wave. Of course, in our situation, it would be the all oscillator synchronizing phase. Okay, so this is one situation. You can also observe the situation quite unexpected, in which only one of you, but not nearest neighbors, are leaving the area of synchronous one and starting to behave different. So such a situation we started to call a solitary state. Okay, you can find the evolution in time of such a situation. So you can find that some solitary states exist for the limited period of time, some existing for the much longer period. You can observe the same with the Chimera state, and this is something which we started to call the imperfect Chimera state, because in this region of perfect synchronization, you can have some elements which are behaving differently. Okay, where else you can find it? So we took another experiment. We took the ring like it. Imagine that you have a candelabra hanging from the wall, and you have a number of excited pendula hanging from it. And in such a situation, you will be able to observe, first of all, the sinusoidal wave. So this would be this perfect synchronization, perfect in-phase synchronization of all oscillators. You can have traveling Chimera. So you can see that those indicated in red are synchronized, those the blue are unsynchronized, and you can see that this red interval is moving around the ring. So this is another situation. Speak a little bit faster. So you can also observe this type of behavior when I think one of my students, David Dudkowski, who was playing very much with the systems of coupled pendula, and he also imagined the devil wheel. You can see the devil wheel in the amusement parks. So imagine that you are sitting somewhere here in the pendulum, and you want, of course, to have excitement, but you want to be safe. And you don't like to have a situation like this, from which you can fall down. And he proved in his experiments that playing with this devil, you can observe that there will be a situation in which some pendula would behave differently. Maybe this is not so important, but such a situation will be very dangerous. Yes, you can see how this can be simulated. So you can see that there are some pendulas which are behaving completely in different way than those synchronous. At this point, we have the question. Of course, nowadays, it is not so difficult to play with the large system. You can have in simulation a system of 100 pendula. You can have a system of 1,000 pendula. All depends on how powerful computer you have. But you can ask a different question. How small would be the Chimera? And of course, the smallest possible one is the three elements. You can have the group of synchronized, so at least two of them should be, and one which is behaving differently. We had at the initial point, we had the rig in which there were 4 double pendula coupled by this green springs here. Originally, this rig was designed for the problem of extracting energy from the seaway, but we played a little bit with it. The double pendulum, the lower bob can rotate or oscillate around this axis. The upper bob can only oscillate around this axis. So we've managed to observe the interesting behavior in which the 4 identical pendula can behave differently. You can see the 2 are nicely synchronized. One is synchronized with them, but this one is in antiphase to those 2. The 4th one is behaving completely differently. Okay, here it will be even more interesting case in which you will be able to observe the coexistence of the rotational motion of 3 of the pendulum and only oscillatory motion of 1 of them. And please remember that all pendula are the same. We've been trying to keep the same parameters for all of them, but this situation, of course, depends on the initial conditions. In such experiments, we've been unable to control exactly the initial conditions. No, but anyway, the initial conditions which are leading to the chimera behavior are quite typical. Okay, going back to metronomes, we took 3 of them. You can play with 3 of them easily. We coupled them by lycra bands like this. What is the possibility? Now I think you can also hear that 2 of them, 3 and 3, are synchronized. The one is behaving differently. So this is the smallest chimera state we've been able to observe. And you can see here 2 of them, this blue line here, they are oscillating. The 3rd one is oscillating with a much smaller amplitude and not related to the other. I think we observed the same behavior both in experiments and in simulations. Skip it. Later, we've been trying to push them to repeat the same chimera state for 3 metronomes, but using a different coupling. We introduced the magnetic field to couple the pendula together, and the result was more or less the same. 3 metronomes, we've been able to observe that 2 of them are synchronized and oscillating at the same frequency, like the 3rd one is oscillating with a different frequency. And also the very interesting thing we did at the end, I think we still managed to briefly tell this. We took the number of double pendula on the platform, and the platform is just forced vertically with the fixed amplitude and fixed frequency. And it is possible to observe synchronization of all pendula. And you can also observe the interesting situation in which when the pendula are not coupled, only located on this platform, you will be able to observe the permanent chaotic motion of them. So here you can see how this was located on the V. And you can observe that finally, the situation would be like this, that all of them will start to rotate. But going to this situation, it will start with the chaotic motion, 3 of them. After some time, 1 of them became the regular motion, the second will join them, and finally, all of them would rotate. But in between, of course, there will be mechanics. So we did experiments for free double pendula, we did simulation for 50. Okay, so I think I will finish with this one. I will show you that it is possible to observe the chaotic motion for the significantly long period of time. So you can see here in this movie that for a few thousands of periods of excitation, a few thousands of the motion is stable, both double pendula would oscillate in the chaotic way. There was another experiment in which you will see that originally they are starting with 3 of them chaotic. After some time, you will observe that 1 of them will start to rotate. After another significant period of time, the second one will join. And at the end, 3 of them would rotate in the regular way. So the first one started to rotate. Rotating, but when you return the direction, I think after 2 seconds, you will observe that the different one would also rotate. Of course, this is just few seconds in the movie. In the real experiment, it was much longer period of time. Okay, finally, we've been very much surprised when Jürgen Kurz came to us and he told, okay, we can use this experiment to explain the blackout phenomena. I think you know that the blackout is the phenomena in which suddenly, for unexpected reasons, there will be no electricity and a big area of land. Blackouts from time to time occurring. The people are not knowing the origin of blackout. The electrical engineers just know how to repair the system of the blackout. And I think that the blackout can be explained by the creation of Chimera state, or particularly by the creation of special type of solitary state. I think that my time is over, so I will just skip all this. We played a little bit on Scandinavia power grid because it is very difficult to get the real model of the power grid. Of course, it's for the known reason, this is secret, even for the scientists. We cannot get it. In Scandinavia, they created something which is perhaps similar to the real power grid of Scandinavia, and this is the power grid on which all experiments are done. Okay, so we can skip. This is my dog. I painted her myself. Thank you very much for your attention.
Thank you very much. Do you have questions?
I have a question. Right now, the very popular topic has to do with the quantum computation. So there is a kind of natural oscillator, a quantum oscillator, which is subjected to decoupling from this interacting with environment. So the question is it possible that certain number of qubits with certain logical density would naturally different from the coherence from outside due to some synchronization mechanism?
I don't know very much on quantum system, but perhaps it is possible.
So let's say if you construct a quantum computer that has 1 million qubits, it could be much more less sensitive towards external noise than a system of 10 qubits. Is it possible in that case? Is there any hint from your side or any clue in methodology that I should search for?
Okay, I think that generally it is easier to desynchronize the larger system than smaller. No, but I think I cannot speculate much more about this.
Okay, I have a second question. There is a phenomena which is known as quasi-stationarity, quasi-periodicity. There is Professor Jacek Leszkow from Politechnika Krakowska, who studied this phenomena. Can you account for some analytic approach towards quasi-periodic systems? So usually a system that is perturbed in a very small way is considered as a quasi-stationary. So can you make any hints on such systems dynamics?
Okay, I was playing a little bit with such systems many years ago. I was considering the systems which are forced by quasi-periodic forcing. So I took the two external forces which were incommensurate together. And in such case, it is possible to observe not only the strange chaotic attractors, but also something which we call the strange non-chaotic attractors. So the structure is fractal, there is no periodicity, but the Lyapunov exponents are negative. So this is what can be done analytically with the quasi-periodic systems. I think you can try to use any approximate analytical methods which are used for the periodic forcing, just adding the second term. But I'm not sure. Okay, such methods are not accurate even for the periodic force. I think you should have, always telling to the students that you should have also the nose. So you have to understand your system, just to be sure that this approximate method has any connection with the real behavior of your system. In many cases, there is no. I think you perhaps know these methods of the small parameters. So nobody would never ask you, nobody would never answer you the question how small parameter can be. Of course, it should be less than 1 to have the convergence of the time series, but it should be significantly less than 1. And how significantly depend on the particular problem you are considering.
Thank you for answers and thank you for great presentation.
Do you have a question? Maybe the last one comment. In case of the photovoltaic systems, we have many source generator in the network. So we have many clocks.
Yeah. I think that, okay, our study which we did on the power grids, at least on this theoretical Scandinavian power grid, is very surprising. So it is very difficult. Okay, it is very easy to destabilize the power grid by disconnecting the consumer. So you mean what this means? the one is not paying the bills, electricity cannot disconnect him because they can destabilize the network. Of course, this is a joke, yeah? But in some cases, we proved that disconnecting of the consumer is more difficult for the stability than disconnecting of the generator. Of course, there are many generators.